Now we are going to talk about functions in Julia. But what is a function? A function is a collected group of instructions that can return one or more values, possibly based on the input arguments. If the arguments contain mutable values like arrays, the array can be modified inside the function. By convention, an exclamation mark at the end of a function's name indicates that the function may modify its arguments. There are various syntaxes for defining functions. When the function contains a single expression, when the function contains multiple expressions, when the function does not need a name. Single expression functions. To define a simple function, all you need to do is provide the function name and any arguments in parentheses on the left and an expression on the right of an equals sign. These are just like mathematical functions. For example, I defined f equal to x squared function and I passed the value 2 and get the value 4. Now I defined a multivariable function gxy which calculates the square root of x squared plus y squared. Then I pass the value 3 and 4 to it and calculate the value. Functions with multiple expressions. The syntax for defining a function with more than one expression is like function, function name, and then you pass the arguments, and in the function's body there are several expressions and it ends with the end keyword. Here's a typical function that calls two other functions and then ends. Here I define the function breakfast and call two other functions make toast and brew coffee. Whatever the value returned by the final expression, here I mean the brew coffee function, that value is also returned by the breakfast function. You can use the return keyword to indicate a specific value to be returned. For instance, I defined a function can pay the bills and pass the bank balance argument to it. If bank balance is less than 0, I return false, else I return true. Some consider it good style to always use a return statement, even if it's not strictly necessary. Later we'll see how to make sure that the function does not go adrift if you call it with the wrong type of argument. Returning more than one value from a function. To return more than one value from a function, use a tuple. For instance, I defined a function double 4 and return a tuple of 2 4s, optional arguments and variable number of arguments. You can define functions with optional arguments so that the function can use sensible defaults if specific values are not supplied. You provide the default symbol and value in the argument list. For example, here I define a function called xy pose and pass the arguments x, y, and z and set the z to the default value 0. Then I print the x, y, z arguments passed to the function x, y, z pose. And when you call this function, you don't provide a third value. The variable z defaults to 0 and uses the value inside the function. I tested with two different arguments. The first one I passed the value 1, 2 to it, and the other one I passed the value 1, 2, 3 to it, and then print the arguments. Keyword and positional arguments. When you write a function with a long list of arguments like fpqrstu, sooner or later you'll forget the order in which you have to supply the arguments. For example, it can be f and pass the string 42 and minus 3.143 and etc. or the other one. You can avoid this problem by using keywords to label arguments. Use a semicolon after the function's unlabeled arguments and follow it with one or more keyword equal to value pairs. For example, over here I define a function f and pass the p and q arguments, and after the semicolon I default the value of the r argument to 4 and s argument to the string hello. Then I print the p and q and return the r and s value. Then call this function expects two arguments and also accepts a number and a string labeled r and s. If you don't supply the keyword arguments, their default values are used. However, If you supply a keyword argument, it can be anywhere in the argument list, not just at the end or in the matching place. When defining a function with keyword arguments, remember to insert a semicolon before the keyword value pairs. Here's another example from the Julia manual. The RTOL keyword can appear anywhere in the list of arguments, or it can be omitted. A function definition can combine all the different kinds of arguments. Here's one with normal, optional, and keyword arguments. Functions with variable number of arguments. Functions can be defined so that they can accept any number of arguments. For example, I defined a function fvar and passed the args 3 dots to it. The 3 dots indicate the famous splat. Here it means any, including none. You can call this function with any number of arguments. For example, I can call the fvar function without any arguments or 0 number of arguments. Or I can pass 1 argument to it, 2 arguments to it, and 3 arguments to it, and so on. Here's another example. Suppose you define a function that accepts 2 arguments. You can call this test function in the usual way. If you have 2 numbers but in a tuple, then how can you supply a single tuple of numbers to this 2 argument function? Again, the answer is to use the ellipsis or a splat. That is, I pass the tuple to the test function and I follow the tuple with 3 dots. The use of ellipsis or a splat is also referred to as splicing the arguments. You can pass a list to the test function also and use the splat operator. You can also combine the map function with the splat operator and a list. For example, pass the 4 and 6 arguments to the test function, local variables, and changing the values of arguments. Any variable you define inside a function will be forgotten when the function finishes. For example, I define a function test and pass the arguments a, b, c to it, and then calculate the subtotal, that is the summation of the a and b and c, and return the value. However, if I call the function test and after that call the variable subtotal, I get the undefined variable error, subtotal not defined. If you want to keep values around across function calls, then you can think about using global variables. A function cannot modify an existing variable passed to it as an argument, but it can change the contents of a container passed to it. For example, here's a function that changes its argument to 5. Although the x inside the function is changed, the x outside the function is not. Variable names in functions are local to the function. But a function can modify the contents of a container, such as an array. This function uses the opening bracket, colon, closing bracket syntax to access the contents of the container x, rather than change the value of the variable x. Here I define the function filled with 5 and use the aforementioned syntax to access the contents of the x container. I create an array x and pass it to the fill with 5 function. The function fill with 5 modifies the content of the container x. You can change elements of the array, but you can't change the variable so that it points to a different array. In other words, your function is not allowed to change the binding of the argument. Anonymous functions. Sometimes you don't want to worry about thinking up a cool name for a function. Anonymous functions, functions with no name, can be used in a number of places in Julia, such as with map and in list comprehensions. the syntax uses dash greater than like this. X dash greater x squared plus 2x minus 1, which defines a nameless function that takes an argument, calls it x, and returns the x squared plus 2x minus 1. For example, the first argument of the map function is a function, and you can define a one-off function that exists just for one particular map operation. For example, I can pass the anonymous function as the first argument to the map function and pass a list of arguments as the second argument to the map function. After the map finishes, both the function and the argument x have disappeared. So if I call the x variable, I'll get the message that x is not defined. If you want an anonymous function that accepts more than one argument, provide the arguments as a tuple. For example, I can define a function which is anonymous and pass it as the first argument to the map function, and pass as the second, third, and fourth arguments of the map function. I can pass 3 lists of numbers. Note that the results are 12, 15, 18 rather than 6, 15, and 24. The anonymous function takes the first value of each of the 3 arrays and adds them, followed by the second, then the third. In addition, anonymous functions can have 0 number of arguments if you use an empty tuple. For example, I can define an anonymous function and assign it to the variable named random. Map. If you already have a function and array, you can call the function for each element of the array by using the map function. This calls the function on each element in turn, collects the results, and returns them in an array. This process is called mapping. For example, I define a vector from 1 to 10 called a and map the elements of a to the sinus function. Map function returns a new array, but if you call map exclamation mark opening and closing parentheses, you modify the contents of the original array. Often you don't have to use map to apply a function like sign to every member of an array, because many functions automatically operate element-wise. The timings of the 2 different versions are similar. Sign dot opening and closing parentheses function has the edge perhaps. Comparing the performances, depending on the number of elements of the argument that is passed to these functions. We can compare the performance of the map function and sign dot by using the add time and comparing the results. Map function collects the results of each application in an array and returns the array. Sometimes you might want the mapping action, but you don't want the results returned as an array. For this job, use for each. For example, I use for each print line and pass an array, and the result will be printed. But if you check the ans or answer variable, you see that it is equal to nothing. And this shows that the results are not returned as an array. Map with multiple arrays. You can use map function with more than one array. The function is applied to the first element of each of the arrays, then to the second, and so on. The arrays must be of the same length, unlike the zip function, which is more tolerant. For instance, over here I use the map function and illustrate an example. Reduce and folding. The map function collects the results of some function working on each and every element of an iterable object, such as an array of numbers. The reduce function does a similar job, but after every element has been seen and processed by the function, only one is left. The function should take 2 arguments and return 1. The array is reduced by continual application so that just 1 is left. A simple example is to use the reduce to sum the numbers in an iterable object, which works like the built-in function sum. For example, reduce plus and passing the array from 1 to 10 returns the sum of them, which is 55. Internally, this does something similar to this. It sums 1 and 2, then sums the result of 1 and 2 with 3, and the result of that with 4, and so on. After each operation adding two numbers, a single number is carried over to the next iteration. This process reduces all the numbers to a single final result. A more useful example is when you want to apply a function to work on each consecutive pair in an iterable object. For example, here's a function that compares the length of two strings and returns the longer one. This can be used to find the longest word in a sentence by working through the string pair by pair. For example, we call the reduce function and pass the function that we've already defined, which is L, and as the second argument, we pass the array of these strings by using the split function and passing the string that we want to actually convert it to an array and check the results. You can see the longest word is the sentence word. Julia offers two related functions, fold L and fold R. These offer the same basic functionality as reduce. The differences are concerned with the direction in which the traversal occurs. In the simple summation example that we have shown, our best guess at what happened inside the reduce operation assumed that the first pair of elements were added first, followed by the second pair, and so on. However, it's also possible that reduce started at the end and worked towards the front. If it's important, use fold L from left to right and fold R for right to left. In many cases, the results are the same, but here's an example where you will get different results depending on which version you will use. However, if you want to use reduce and fold L or fold R functions for functions that take only one argument, use a dummy second argument. For example, over here reduce xy, which returns the square root of x. We pass the array from 1 to 4, and we actually pass a dummy argument also. As you can see, the result is 1.4 blah blah blah, which is equivalent to calling this square root function 4 times. Functions that return functions. You can treat Julia functions in the same way as any other Julia object, particularly when it comes to returning them as the result of other functions. For example, let's create a function making function. Inside this function, a function called new function is created, and this will raise its argument y to the number that was originally passed in as the argument x. This new function is returned as the value of create exponent function. Now we can construct lots of exponent making functions. First, let's build a squarer function and a cuber function. While we are at it, let's do a raised to the power of 4 function called quader, although I'm starting to struggle with the Latin and Greek naming. As you can see from the examples that I'm running, these are ordinary Julia functions. The definition of create exponent function above is perfectly valid Julia code, but it's not idiomatic. For one thing, the return value does not always need to be provided explicitly. The final evaluation is returned if return is not used. Also, in this case, the full form of function can be replaced with the shorter one-line version. This gives the concise version of the create exponent function. Function chaining and composition. Functions in Julia can be used in combination with each other. Function composition is when you apply two or more functions to arguments. You use the function composition operator O to compose the functions. You can type the composition operator at the REPL using \circ or circ, which is probably the short form for circ. For example, the square root function and the plus function can be composed like this, which actually, this composition actually adds the numbers first, then finds the square root. This example composes 3 functions, first, reverse, and uppercase, and we pass the composition of these functions to the map function as the first argument and an array of strings as the second argument by using a split function and passing in a string, a sentence to it. Function chaining, sometimes called piping or using a pipe to send data to a subsequent function, is when you apply a function to the previous function's output. For example, over here I create an array from 1 to 10 and pass it to the sum function, then to the square root function, where the total produced by sum is passed to the square root function, obviously. The equivalent composition would be piping can send data to a function that accepts a single argument. If the function requires more than one argument, you may be able to use an anonymous function. Methods. A function can have one or more different methods of doing a similar job. Each method usually concentrates on doing the job for a particular type. Here's the function to check a longitude when you type in a location. The message generic function with one method. You see, if you define this in the REPL, tells you that there is currently one way you can call the check longitude one function. If you call this function and supply a number, it works fine. But what happens when you type in a longitude in, say, the format seen on the Google Maps? You see, the method error no method matching is less in 64 and the string. The error tells us that the function has stopped because the concept of less than, which we are using inside our function, makes no sense if one argument is a string and the other a number. Strings are not less than or greater than integers because they are two different things, so the function fails at that point. Notice that the check longitude one function did start executing though. The argument LOC, that stands for location, could have been anything: a string, a floating point number, an integer, a symbol, or even an array. There are many ways for this function to fail. This is not the best way to write code. To fix the problem, we might be tempted to add code that tests the incoming values so the strings are handled differently. But Julia proposes a better alternative: methods and multiple dispatch. In the case where the longitude is supplied as a numeric value, the LOC or location argument is defined as being of type real. Let's start again and define a new function and do it properly. Now, this check longitude function does not even run if the value in LOC isn't a real number. The problems of what to do when the value is a string is avoided. With a type real, this particular method can be called with any argument provided that it is some kind of number. We can use the applicable function to test this. Applicable lets you know whether you can apply a function to an argument. That is, whether there is an available method for the function for arguments with that type. The false indicates that you cannot pass a string value to the check longitude function because there is no method for this function that accepts a string. Now the body of the function isn't even looked at. Julia does not know a method for calling check longitude function with a string argument. The obvious next step is to add another method for the check longitude function, only this time one that accepts a string argument. In this way, a function can be given a number of alternative methods, one for numeric arguments, one for the string arguments, and so on. Julia selects and runs one of the available methods depending on the types of arguments you provide to a function. This is actually multiple dispatch. Now the check longitude function has two methods. The code to run depends on the types of the argument you provide to the function, and you can avoid testing the types of arguments at the start of this function. Because Julia only dispatches the flow to the string handling method if LOC is a string. You can use the built-in methods function to find out how many methods you have defined for a particular function. As you can see, there is a large number of methods defined for the plus function. Obviously, something in matrix calculus and different libraries of linear algebra and etc. Julia chooses the most specific method to handle the types of arguments. In the case of check longitude, we have two specific methods, but we could define a more general method and specify the type of LOC as any. This method of check longitude is called when the LOC argument is neither a real number or a string. It's the most general method and won't be called at all if a more specific method is available. Type parameters in method definitions. It's possible to work with type information in method definitions. Here's a simple example. I define the function test and say that if the type of the argument that is passed to the test function is a subtype of real, then it is a valid argument and the function can actually process it. The test method automatically extracts the type of the single argument A passed to it and stores it in the variable t. For this function, the definition of t was where t is a subtype of real, so the type of t must be a subtype of the real type. It can be any real number, but not a complex number. T can be used like any other variable. In this method, it's just printed out using a string interpolation, and it doesn't have to be t, but it nearly always is. This mechanism is useful when you want to constrain the arguments of a particular method definition to be of a particular type. For example, the type of argument A must belong to a real number supertype. So this test method doesn't apply when A isn't a number, because then the type of the argument isn't a subtype of real. For example, I passed a string and I got an error. I passed an array, I got an error again, and the function test cannot handle this. Here's an example where you might want to write a method definition that applies to all one-dimensional integer arrays. It finds all the odd numbers in an array. But because of the way it's defined, it cannot be used for arrays of real numbers. For example, if I pass 10.0 as the last element of the list, we'll get an error. Note that in this simple example, because you are not using the type information inside the method definition, you might be better off sticking to the simpler way of defining methods by adding type information to the arguments. For example, I can define the findOdds function by specifying the type of the argument as an array of int64. But if you wanted to do things inside the method that depended on the types of the arguments, then the type parameters approach will be useful. If you are enjoying the content, don't forget to hit that like button and subscribe for more awesome videos. Your support means the world to me.